previous few sessions, we looked at some very basic ideas on electrostats, got familiar with Coulomb's law, computation of electric field, some basic Gauss's law, etc. About time, we got acclimatized to some basic problem solving on electrostats. This sheet titled Electrostatic Sheet 1 will breed some very basic familiarity with the ideas that we have learned in theory. Once we are done with this sheet, we would have the confidence to move on to the next level of problem solving. But let's look at this to begin with, right? So, electrostatics sheet 1. Sheet 1. Now, the first problem of the sheet is about two fixed charges placed on the y-axis, a charge q placed at 0, a, another identical positive charge q placed at 0, minus a, and a third positive charge which is moving. This is a fixed positive charge, this is a fixed positive charge. But at the origin, we have a charge q naught which could move. We have a charge q naught which could move. Now, initially when it's at the origin, the electrostatic repulsion between this q and this q naught is balanced by the electrostatic repulsion between this q and this q naught, and therefore it is in equilibrium. Now, what's given is this charge q naught is slightly displaced from the origin. This charge q naught is slightly displaced from the origin and is brought to this position and released. Now, once somebody does that, what really transpires is that there is electrostatic repulsion between the upper q and q naught. This is the direction of electrostatic repulsion. And this q and q naught, there is going to be another electrostatic repulsion. And there would be forces F and F equally inclined with the x-axis from this charge and this charge. Consequently, the resultant of these two forces is going to be a net leftward force F naught acting on Q naught. And this F naught would cause Q naught to race away to infinity. Q naught would keep giving up its potential energy and would keep gathering kinetic energy. At infinity, its potential energy would become 0 and its kinetic energy would be the maximum it could be. That's the whole idea, right? So this problem, which asks you to compute the speed of the particle at infinity, requires you to be able to apply the very basic energy principles, converting potential energy at O to kinetic energy at infinity. That's the whole idea. Fair and simple. Now, the potential energy of Q naught in this slightly displaced position is almost the potential energy of Q naught at O. So that's an approximation. In order to compute the potential energy at Q naught, we rather at this position, we rather compute the potential energy of Q naught at O. Now, how does one compute the potential energy of Q naught at O? Compute the potential at O because of this Q, compute the potential at O because of this Q, and multiply the net potential at O with Q naught to get the potential energy of Q naught at O, which is also going to be the potential energy of Q naught in this slightly displaced position, right? So the potential at O is what? Because of the upper charge, kq by A. Because of the lower charge, another kq by A. So 2 kq by A, right? That's the potential energy at O because of, that's a potential at O because of the upper and the lower charge. So the potential energy at O is going to be this into Q naught. That's going to be the total potential energy. And this gets completely converted into kinetic energy when this charge Q naught races away to infinity. So this gets converted into kinetic energy of the charged particle at infinity. Put k equal to 1 by 4 pi epsilon naught and solve for the speed of the particle v at infinity. This is all that it requires, right? Very basic, simple principle. So next few problems are also as simple as this. So I would expect you to attempt these problems, and then we would interactively solve these problems. Once we are done with these problems, it would be the ground would be ripe for us to move to the next level of problem solving. So hopefully by the end of this class we would have finished all these problems. This much. Please wait. I would rather wait till you attempt the next problem. Let's look at 1b. If it was a negative charge, it wouldn't have yes. If it was displaced slightly from the mean position, yes. Like you saw in the ring, along the ring. So yes, it'll oscillate. One B. There is a hemisphere centered at O and of radius R. And this has surface charge density sigma. The surface charge density on the hemisphere is sigma. We then want to be able to compute the potential at this point, vertex A of this hemisphere. Want to be able to compute the potential at the vertex A of this hemisphere, given that the hemisphere has surface charge density sigma and has radius r. Clear? Now what we could do is we could break the hemisphere into rings. The surface could be broken down into rings. This is a certain ring. Several such rings with a common axis, several such rings with this being the common axis will constitute the hemisphere, right? So this is one chosen ring. For this chosen ring, I compute the potential at the point A, and I sum up the potentials because of various rings that constitute this hemisphere. That's what we want to be able to do. Right. So first of all, I should be able to locate this ring, right? So all the rings that constitute this hemisphere can be located by this angle theta. Theta running from 0 to pi by 2 will locate all the rings that constitute the hemisphere. Theta running from 0 to pi by 2 would cover the entire hemisphere, right? Now to designate the thickness of the hemisphere from this point to this point, let's say the variation in theta is really small and is d theta. Consequently, the thickness of this ring is going to be r d theta, right? Also, you want to be able to see that if there is a ring that is selected at an angle theta, the radius of the hemisphere is r. So the radius of the ring is going to be r sine theta, is going to be the radius of the ring, right? That's going to be the radius of this ring. Yes or no? Right? So the circumference of this ring is going to be 2 pi into small r, which is r sine theta. That's the circumference of this ring. The charge on this ring, okay, now the surface area of this ring is circumference into r d theta. Into sigma will give me the charge on this ring. Will give me the charge on this ring, yes or no? Now, so if there is this ring, I know the charge on this ring, and I want to be able to compute the potential at this point A. This is theta. Then realize that this is r. OA equals OB equals r. Then the slant height of the cone of which this ring forms a part, right? This is the ring. And this is the slant height of the cone of which this ring forms a part. Clear? How about it? Right? So K times the charge on the ring divided by slant height of the cone will give me the potential at A. Right? To calculate the potential at A because of this ring, I want to be able to do K times the charge on this ring, this is the charge on the ring, divided by this x, which is the slant height of this cone constituted by this ring, kq divided by this x. Now to calculate this x, see cosine rule, x squared equals this r squared plus this r squared, which is 2r squared minus twice this into this, that is 2r squared into cos theta, which is like 2r squared into 1 minus cos theta, which is 2 sine square theta by 2. So x then turns out to be 2r sine theta by 2. Yes or no? 1 minus cos theta is 2 sine square theta by 2, right? So x, then the slant height of this cone turns out to be 2r sine theta by 2. So k times the charge on this ring divided by the slant height of the cone, which is 2r sine theta by 2, will give me the potential at A because of this chosen ring, right? The total potential at A would be sum of all of this, where theta is made to run from 0 to pi by 2. Theta runs from 0 to pi by 2. That gives me the potential at A. That gives me the potential at A. Now, K is 1 by 4 pi epsilon naught. R, sigma, everything will come out. All that you would have to integrate is sine theta divided by sine theta by 2, because the rest all would be a constant which would scoop out of the integral sign. Yes or no? Theta runs from 0 to pi by 2. How do you integrate this? Write this as 2 sine theta by 2 cos theta by 2. So this would be something into 2 sine theta by 2 cos theta by 2 d theta. Theta runs from 0 to pi by 2. The sine theta by 2 will get cancelled from the numerator and denominator, and this can be sine theta by 2 by half. And you can supply the limits and you'll be able to obtain the potential at A. Clear? Confusion? Tell me. This? Why? Okay. See, if there is a ring, and if I took a charge element dq on the ring, right, and this is the slant height of the cone, then what would be the contribution of this charge element on this? K times dq divided by slant height L? Yes or no? The total potential at A would be sum of all of this, and for all the dq's that constitute this ring, L would be the same. You'll have the same distance L from various elements that constitute the ring to the point A. So this is going to be K by L integral dq. Integral dq is the total charge. So this is going to be K by L into the total charge Q on the ring. So the potential at a certain point on the axis of a ring is going to be K times the charge on the ring divided by the slant height of the cone which the ring could constitute with that point on the axis of the ring, right? So in this case, realize that, think of this as the base of the cone, this as the vertex of the cone, this would be the slant height of the cone. So K times the charge on this ring divided by this X would give me the potential at A. Yes or no? Next we have problem C. A rod AB of length L, AB is L, and of mass M is positively charged with linear charge density lambda. That means charge per unit length on this is lambda. Lambda is the charge per unit length on this rod. It is pivoted at A. It's pivoted at A and is hanging freely horizontally like this. Like this. Pivoted at this end, say, and it's hanging freely. Right? Like this. Like this. The electric field is applied this way. Right? So you understand what the situation is? It's pivoted at this end. Right? fixed here like this, and an electric field is applied so that it could move this way on this horizontal surface. You know what I'm saying? Pivoted at this end, horizontal electric field, so that it could rotate like this on the horizontal plane. It can rotate in the horizontal plane. That is what it is, right? Horizontal electric field pivoted at this end and it could move horizontally, right? So now this rod is subject to a uniform electric field E. Right? We want to be able to find the horizontal acceleration of the rod. We want to be able to find the horizontal acceleration with which the rod starts to move about A. See, one thing, what you could do is, you could, yes, take a small element here at a distance x, a small element of length dx, right? The force that this element will experience is going to be E into the charge on this element. Lambda dx is the charge on this element. That's a force that this element will experience. Yes or no? That's a force experienced by this element, right? And this element will experience a torque about A. It's at a distance x from A. So it will experience a small amount of torque, which is the force lambda into dx into x. That's a torque that it experiences about A, right? The total torque experienced by the rod, about A would be sum of all of this. X runs from 0 to L. That's the total torque experienced by the rod. Yes or no? And that's going to be I about A into angular acceleration alpha. It develops an angular acceleration alpha. That's I about A, which is 1/3 ml squared into angular acceleration A. And E and lambda will come out. Lambda E. X dx will give me L squared by 2 is 1/3 ml squared into alpha. Yes or no? Clear? So angular acceleration alpha, it could also have been done without integrating. What you could do is, since it's a uniform electric field, see, let me also tell you, since it's a uniform electric field, what we could have done really is, it experiences a total force. What's the total charge? Lambda into L is the total charge. Since it's uniformly distributed, we could imagine this entire charge to be, let's say, at halfway down the ring, halfway down the rod, L by 2, and it experiences a force. E times lambda L, E times the total charge, that's the force that it experiences, and this force produces a torque E into lambda L into L by 2 is the total torque that it produces about this end A, and that must be I about A, which is 1/3 ml squared into alpha. Right? If, however, right, do you understand that? So for a uniform exposure to an electric field, you can replace the total force by a single force halfway down the rod and apply torque about this end, right? However, if the field was not uniform, say we had a field that varied this way. This is, say, x equal to 0 to x equal to L. This was the field. This is how the field varied. And the field at x equal to L was, say, E naught. Suppose this is how the field varied. So then, each element will be exposed to a different value of the electric field, right? So for example, the element at X would be exposed to an electric field E at X, right? And as you can again see, E at X is going to be E naught by L into X. Do you realize that? This divided by this is going to be L divided by X, similar triangles, right? So E at X would be a function of X given by this. So the force experienced by this chosen element at X, the force experienced by this chosen element is going to be lambda into dx, which is the charge on this, into E at X is going to be the force that this chosen element experiences, right? The torque that it experiences about A would be this into X, is going to be the torque that it experiences about A. The total torque about A would be sum of all of this, where X runs from 0 to L. So in this case, of course, lambda, again, lambda itself could be a function of X. If it's a non-uniform distribution of charge, then lambda would be a function of X. You can plug in that lambda a function of X, E a function of X obtain, and integrate this whole thing, supply the limits, X equal to 0 to L, and this must be I about A into alpha. I about A is going to be 1/3 ml squared into angular acceleration alpha. Right? So this would take care of a variable lambda. This would also take care of a variable field. Clear? Problem D. The electric potential V at any x comma y in the xy plane is given as minus some constant k times xy. The electric field intensity at a distance r, from the origin, that means this is the x-axis, this is the y-axis, at a distance r from the origin, what is the intensity of the electric field? That is what we need to find, right? Now realize that the x component of the electric field is always given by minus dou v dou x, right? Which is like k times y. The electric field in the y direction, the y component is given by minus dou v dou y, which is k times x. The electric field at any point P, whose coordinates are x comma y, is going to be given by root Ex squared plus Ey squared, which is root k squared into x squared plus y squared. But x squared plus y squared is r squared. So this would be given by mod k, root k squared is mod k times r. So the electric field at any point P will be proportional to r, will be directly proportional to r, the distance from the origin for this situation, right? Root k squared will always be mod k, isn't it? Why? Where is it said that it has to be positive? This k is not 1 by 4 pi epsilon naught. This k is just some constant, right? The next problem. A positive charge plus q is uniformly distributed in the xy plane, defined in a region given by x squared plus y squared less than or equal to b squared greater than or equal to a squared and z equal to 0. Now x squared plus y squared equal to b squared is a circle with center 0 0 radius b. X squared plus y squared equal to a squared is a circle with center origin and radius a. This is the region between the two circles lying in the xy plane. Z equal to 0 is the xy plane. Yes or no? Right? So this essentially, this region is given by an annulus in the xy plane. This is the z direction. This is the z axis. And this region is given by this annulus, region between these two circles of radius A and B. Radius A and B. This is the region. And in this region, there is a total amount of charge, capital Q, uniformly distributed. That means in this region, the charge per unit area is uniform. Charge per unit area is given by Q by pi B squared minus A squared. Right? That's the charge per unit area uniformly distributed in this region. Yes or no? Right? Now, there is a positive point charge Q which is projected from a point P on the z-axis at a very large distance from the origin. At a very large distance from O, there is a positive charge plus Q which is projected towards the sheet. What minimum speed must be imparted to this? What must be V minimum that must be imparted from the origin so that it does not return to P, so that this particle does not return to P? So let's first try and understand why would it have a propensity to return to P. Very simple. This is positive charge, uniformly distributed. This is a positive charge. When you impart it a velocity V, this will experience repulsion from this charge, right? So the velocity of this will keep depleting, right? Now, on before reaching O, suppose it reaches the point P prime where the velocity becomes 0. If the velocity of this particle becomes 0 before it reaches O, then it will return back to P. However, if it just about crosses O, see, if its velocity is large enough and it doesn't get depleted on reaching O, say it goes below the ring, say it goes below the surface defined by this, then it will experience repulsion in the downward direction and will never return to P. Right? So we must at least have a certain velocity which does not get depleted before reaching O. The minimum V would be such that the velocity just about gets depleted on reaching O. That will give us the model for the minimum V that you must impart to the charged particle Q. Right? Yes or no? So let's say I give it a velocity V such that on reaching O, its velocity becomes 0. Now, if I give it a velocity larger than that velocity, then the velocity will become 0 on crossing O. Then it will go down and will get repelled in the downward direction and will never return to P. Okay. So then, at P, since P is very, very large away from the origin, the potential is 0. At this point, the potential is 0. At this point, on reaching O, the particle has a certain potential energy. So what I'll do is between P and O, at P there is only kinetic energy. At O, kinetic energy will become 0 and there will be only potential energy. So I need to be able to compute the potential at O because of this distribution, so that I could obtain the potential energy of Q on reaching O. Yes or no? Right? So let me compute the potential at O because of this distribution. This is radius A. This is radius B. Right? What I do is, I break this entire disk into smaller rings. This is a small ring. This is a small ring of radius R and of thickness dr. This is a small ring centered at O of radius R and thickness dr. Right? What's the circumference of this ring? 2 pi r is the circumference of this ring. What's the area of the shaded portion of this ring? Into dr. What's the charge on this ring? Into sigma. Now, the potential at O is going to be K times the charge on this ring divided by the radius of this ring, because all points on the ring are at the same distance r from the ring. So, the potential at O is going to be K times potential at O because of this chosen ring is going to be K times the charge on this ring divided by the radius of this ring divided by the radius of this ring. Yes or no? That's going to be the potential at O because of this chosen ring, right? The total potential is going to be sum of all of this. The total potential is going to be sum of all of this, where R runs from A to B. That's going to be the potential at O. So very clearly this then becomes 2 pi K sigma into B minus A. 2 pi K sigma. R will get cancelled into B minus A. So then, now when this particle from infinity, that is at this point P, is launched with a velocity V, at P what does it have? Zero potential energy, and it only has kinetic energy. At O, if its velocity just about becomes zero, it only has potential energy. The potential energy is going to be Q times U naught, where U naught is computed from those considerations, and this will give you the required V. This will give you the required V. Yes or no? So if you impart it a velocity V given by this equation, it reaches O with zero velocity, right? If you give it a velocity slightly greater than V, the velocity of this particle will become zero after having crossed O in the downward direction, and the moment it goes below the sheet, it will get repelled in the downward direction and will never be able to return to P. So any V slightly in excess of this V is good enough. So the minimum V is this. Minimum V that you must impart to the particle is this. Clear? Now, let me look at F. There is a spherical region. There is a spherical region in which charge is distributed. Where at a distance r from the center, the volume charge density would be a function of r. At a distance r from the center of this region, the volume charge density would be a function of r alone. Now, it is found that the numerical value of E in this entire region is the same. It is found that the numerical value of E in this entire region is the same. We want to be able to figure out how rho varies with R in this region for this to ever happen. For this to ever happen, how should rho vary with R? So that numerically the value of the electric field in this region is the same for all R. Yes or no? This is the problem to be investigated. Clear? Now, see, if I think of a sphere in this region of radius small r. Sphere in this region of radius small r. Okay. Then, since rho depends only on r, rho depends only on distance, that means you would expect E to be, of course, E is given to be numerically the same at all points, and because of symmetry considerations, E would be radially outwards at every point. E would not only numerically be the same, E is numerically the same because that's given. Because of symmetry considerations, E would be radially outwards on this chosen spherical surface. Yes or no? This is my Gaussian surface. This is my Gaussian surface. Now this encloses a certain amount of charge. This encloses a certain amount of charge. The total flux through this Gaussian surface would be equal to charge enclosed by epsilon naught. Right? Now, on each of these elements, realize that E and the normal are in the same sense. So E dot ds would be simply E into ds, E into ds, E into ds, E into ds. So the total flux through this would be E into surface area of the sphere. E into surface area of the sphere is going to be the total flux that will pass through the surface. So the total flux that passes through the Gaussian surface GS is going to be E into 4 pi r squared. And that must be equal to charge enclosed by epsilon naught. That must be equal to charge enclosed by epsilon naught. So the next task is to be able to find charge enclosed within the sphere of radius small r. Yes or no? Right? So let's do that. If I look at this separately, this sphere of radius small r, the Gaussian surface, there is charge everywhere distributed inside this. If I think of this as x and the thickness of this as dx, right? I break it up into spherical shells. This entire region of radius small r, I break it up into smaller spherical shells. This is one chosen spherical shell. What is the surface area of this shell? 4 pi x squared. What's the thickness of this shell? Dx. Now, rho will be a function of x. That's given in the problem. Rho is a function of the radius x. So the charge on this in this chosen volume is going to be volume of this region into rho at x. Into rho at x, right? All these points are at x, so they will have the same value of rho, the rho at x. So the volume of the shaded region into the charge per unit volume will give me the charge enclosed in the shaded region. Yes or no? So the total charge in this sphere of radius small r is going to be the sum of all of this, where x runs from 0 to small r. That's the total charge in this region. Yes or no? Right? So this must be total charge 0 to small r, 4 pi x squared rho at x into dx divided by epsilon naught. Right? Now, the key thing here is this last bit for the problem. Can I wipe this off? So far so good? Is there an issue? No? This is simple application of Gauss's law and deploying symmetry and the conditions given in the problem. Now, realize that E should turn out to be independent of R. When I solve E from this equation, it should turn out to be independent of R. It should be numerically the same for all R. We must have that. Such should be rho. Such should be rho. Yes or no? Which means, see, there is a R square here. On integrating here, I should get an R squared so that E becomes independent of R. Yes or no? Yes or no? Right? Now, if I get an R squared, that means I should be able to integrate x. If I integrate x here, if I have only x to integrate here, then I'll get a R square, and this R square and this R square will get cancelled. Yes or no? So again, there is an x square here. There should be some x sitting in the denominator so that we have only x to integrate. When I integrate only x, I'll get only r squared on the right hand side, which will cancel the r squared on the left hand side, and E will be rendered independent of r. So very clearly, rho x should be some constant c by x. If rho x is some constant c by x, then this x and this x will get cancelled, leaving me with some r square on supplying the limit, and the two r squareds would get cancelled, and E would be independent of r. So this is how rho should be as a function of x. That means as a function of r, distance from the center, it's going to be c by r. This is how rho should vary with r, so that this entire region becomes a region of electric field which has the same numerical value at all points. Right? Rho as a function of r must be c by r then to meet the requirements. So problem G. There is a ball of mass m and charge q in a vertical plane at the end of a string of length L. In a uniform electric field whose lines of force are directed upwards, E upwards in this region, right? What velocity must be given to the ball in the lowest position so that it completes the circle? Right? Now, you know that if E was not there, then the only two forces acting would have been mg and T, and the V minimum to complete the circle in absence of E would have been root 5GL. 5GL would have been the minimum V so that it could complete the circle. Now, realize what happens is, if you look at this mass M, there is mg acting, right? In addition, there is a QE acting. Right now, the effective of these two is like mg minus QE, right? Which is as if there is a G effective, which is mg effective, right? So the G effective for the situation, or the equivalent G for the situation in which there is an electric field acting, is like a G minus QE by M. That means I can replace this situation by one in which, let's say, there is no electric field, but G has become G effective. This is a situation in which instead of G, you have G effective, and there is no electric field. So when I take G effective, it's as if there is no electric field. The effect of the electric field is included in G effective. And then the minimum V that you must impart to it is root 5 G effective into the length L, which is the radius R. So where G effective is given by this. And again, the next part of the problem, what would be the maximum tension in the string? The maximum tension is at the bottommost point, right? So if T is the tension at this point, for which the applied velocity is V minimum, then mg, or rather T minus mg effective will give the required centripetal force directed towards O. That must be m V min squared divided by L. Yes or no? Where V min squared is 5G effective into L plus mg effective, so T would be 6 mg effective, because V min squared is this, so you get T equal to 6 times mg effective, where G effective is G minus QE by M, right? That's the equivalent G. See, all that I'm saying is, if you had an electric field, what's the impact of the electric field? It'll dilute the weight. The new weight effectively will become mg minus QE. That's the new weight. That means the new G is going to be M into G effective. That means I can forget all about E, and instead of G, I deal with G minus QE by M, in which the effect of the electric field is included. All that I'm saying is, well, I don't have to do fresh calculations. I can use whatever I have derived earlier. The minimum velocity that you must impart at root 5GR. So now the G, instead of being the old G, would be the revised or the modified G in presence of an electric field. Then the effect of the electric field is incorporated in it. Got me? I'm talking of G effective. So in G effective, will you look at weight or will you look at tension? Tension was there anyways earlier also, right? So if I have to look at G effective, I would look at mg and the other force, right? T was anyways there in both situations, right? Yes or no? Got me, na? The thin conducting ring of radius small r. Thin conducting ring of radius small r, okay, and has an electric charge plus Q distributed over it. That means there is charge per unit length Q by 2 pi r. There is charge per unit length q by 2 pi r distributed over it. Now, when there is this charge distributed over it, there is no repulsion, nothing. Now what would happen is, if you took a small element on this, say a small element of the ring AB, if you took, just a small element AB of the ring with a charge, say Q naught present at O, what would happen? This charge distributed on AB would get repelled, would have a propensity to move up. Consequently, what really happens is tension in the ring develops such that, and you know, all the tensions between A and B will cancel off. But if I look at the free body diagram of A and B, then the unbalanced tension would be the tension at A and B, right? The horizontal components of the tension will cancel off. The vertical tensions will balance repulsion so that AB remains in equilibrium. That is how things will happen here. You know what I'm saying? That's why this tension develops, so that the vertical component of the tension will balance the repulsion, right? Now, if say this AB is very small, this angle is d theta. So this is going to be d theta by 2. This AB could be replaced by a point charge at P, which is lambda r d theta is the charge at this, right? R d theta is the length of this, into charge per unit length would be the charge at Q, right? That will be almost like the charge at Q, which is, say, dq, right? So then, this is d theta by 2, this is d theta by 2, this is d theta by 2, and similarly on the right hand side, this is d theta by 2, this is d theta by 2, right? 2t sine d theta by 2 would be the vertical component of the tension acting on this AB. 2t sine d theta by 2, right? T sine d theta by 2, t sine. The horizontal components of t will get cancelled off, and this must balance the repulsion between this charge and this charge. That means this charge is, so what's the repulsion between the two charges? K, which is 1 by 4 pi epsilon naught, into Q naught, into this charge, which is lambda r d theta, divided by r squared, where lambda we already know, right? Now, d theta by 2 is very small, so sine d theta by 2 can be replaced by d theta by 2. So this is like 2t into d theta by 2 is kq naught lambda by r squared. So now by r into d theta, where d theta now will get cancelled, and lambda you can plug in as q by 2 pi r, and you'll be able to obtain the tension in the ring once a charge q naught is kept at the center. Yes or no? Lambda is q by 2 pi r, etc. you plug in, and you'll be able to get the required tension. Yes, initially there would be no tension. It's like just slack, slightly better than a slack state. See, if there is just a ring, what would you expect as the tension? So this, you can actually, you know, it depends. This to be technically correct is the increase in tension. This to be technically correct is the increase in tension when the charge, because it's the increased tension that will balance the electrostatic repulsion and maintain equilibrium. So you should rather look upon this as increase in tension, is how you should look at it.
Now suppose if I put a charge Q naught at the center, and if there's capital Q charge on the ring, then what I could do is KQ Q naught divided by R square. That would be the new force.
No, of course not. These forces are in different directions. Each element of the ring would have charge distributed, and force experienced by charges on the circumference would be all radially outward. So these are forces in different directions. So you can't add them up. You can't say the total force is kq q naught by r squared is not the total force, because these are all forces in different directions. How are you adding them like scalars? That will not be the force. There is an electric field E given by 20 I cap plus 30 j cap in space. The potential at the origin is taken to be 0. We want to be able to find the potential at 2 comma 2 at a point 2 meters comma 2 meters. This is where we want to be able to find the potential. That means initial r is r naught, which is 0. The final r is, say, r1, which is 2i cap plus 2j cap, the final position, right? And since it's a uniform electric field, E dot r1 minus r0, this is the work done by the electric field when you take a unit positive charge from r0 to r1. And this must be negative of the change in potential. That means minus of, let's say, let me call this v1 minus v0, negative of the change in potential. Work done by the electric field in a uniform electric field, the work done is going to be E dot final position minus initial position. That's the work done by electric field if it's uniform, right? It's negative of the change in potential, v1 minus v0, right? r0 is 0. E dot means 20 I cap plus 30 j cap dot r1. r1 is 2 I cap plus 2 j cap is minus v1. v1 is what we want to calculate. v0 is given to be 0, right? And as you can see, this is 40 plus 60, 100 is minus v1, or v1 is minus 100 volts. Is the potential at 2 comma 2. Two concentric spheres of radii r1 and r2 have charges q1 and q2 distributed over their surfaces. Find the potential difference between the two surfaces. Let me also assume that these are conducting shells. Let me assume that these are conducting shells, right? Even though it's not given, for the sake of the problem, not for the first part of the problem, but for the next part of the problem, we will have to assume that they are conducting. Because see, if they were non-conducting, then it's going to be a different situation. But let's say for the first part, even if they are conducting or non-conducting, does not matter. If I have to calculate the potential difference between sphere 1 and sphere 2, then whether they are conducting or not will not make a difference. The first part of the problem, for example, where I want to calculate the potential difference, I'm assuming that q1 is distributed uniformly, q2 is distributed uniformly. Whether this distribution is on a conducting surface or a non-conducting surface will not matter. As long as the distribution q1 and q2 is uniform, it does not matter whether it's conducting or non-conducting. It's going to produce the same kind of electric field and potentials in the surrounding regions, right? I've done this problem in the class. Okay, let me still, for the sake of everyone, let me still do it one more time, because it has an important instruction to communicate. So then, what's the potential on 1 because of its own charge? kq1 by r1, right? Now, if q2 is uniformly distributed on the surface, then the potential on the surface because of q2 will be potential anywhere inside. So the potential on the surface of 2 because of its own charge is going to be kq2 by r2, and that's going to be the potential that it produces on 1 as well. So potential on 1 because of q2 is going to be kq2 by r2, right? Now, potential on 2 because of its own charge, kq2 by r2. Yes or no? Plus, now as far as the potential on this is concerned, because of this, I can imagine q1 to be concentrated at the center. So that's going to be kq1 by r2. And now if I take the difference, say potential 1 minus potential 2, kq2 by r2 will get cancelled, leaving me with kq1 into 1 by r1 minus 1 by r2. Which means now if I change q2 to q2 prime, the potential difference will not change. The potential difference between these two surfaces will depend only on the charge on the inner surface, yes or no? It's independent of q2. So if you change q2 to q2 prime, the potential of this will change, the potential of this will change, but the potential difference will remain the same, and it's going to be dependent only on the charge on the inner surface. Yes or no? This is an important result to remember. Now, what happens to the potential difference when connected by a wire? Yes, there would be flow of charge. There would be flow of charge such that the potentials get equalized. Potential difference becomes 0. Now, what happens to the charges? Potential difference, this will become 0. That means charge on the inner surface must become 0. That means there should be no charge resident on the inner surface. This charge q1 would flow to the outer surface. So the inner surface would be deprived of charge. The outer surface would have charge q1 plus q2. Dekho, potential difference is what? K times the charge on the inner surface into 1 by r1 minus 1 by r2. When connected by a wire, this will become 0. So q on the inner surface will become 0. When would q on the inner surface become 0? When q1 rushes to the outer surface. That means there is no charge left in the inner surface. Now, if this happens, then we essentially have the charge on this 0 and the entire charge q1 plus q2 on this. And do you realize the potential on the surface of this is going to be what? kq1 plus q2 by r2, and that's also going to be the potential anywhere inside, which is the potential on the inner surface. Potential difference then would be rendered 0. Now, these calculations are not required. To understand that the charge q1 flows to the outer surface does not require this calculation. Reason being simple. The simple reason is, see, this a conductor, this a conductor, this a conducting wire, right? The whole thing could be looked upon as one single conductor of an awkward shape. So what? The whole unit could be looked upon as a conductor of an awkward shape. Yes or no? Which means no charge can reside inside the conductor. So if there is this charge q1, it will flow to the outer surface. If the cavity does not have any charge, this is the cavity, it does not have any charge. So it will not hold any charge on the cavity walls. All the charge would flow on to the outer surface. So this charge would appear on the outer surface alone.
What would have happened if it was not a conductor?
If it was not a conductor, then if you give it charge q1, it may not necessarily uniformly distribute itself, right? Then all those rules will not apply. 2, if this was a non-conductor and there was charge here and here and here, then there would be no flow. There would be no flow, isn't it? Yes. I mean, if two non-conductors are connected, right, there would be no flow of charge. Now, let me look at L. Let me look at L. There is a uncharged spherical conducting layer having inner radius A and outer radius B. Uncharged conducting layer having an inner radius A and an outer radius B. Find the potential at the center O if a point charge Q is kept at a distance r from O, if a point charge q is kept at a distance r from O, such that r is less than a, that means it's in this region. R less than a means r is in this region. We want to be able to find the potential at the center O. We want to be able to find the potential at the center O. Clear? Now, what would this charge q do? This charge q placed here would induce minus q on the cavity walls. This time non-uniform. Why non-uniform? Because this q is not placed at the center. If it was placed at the center, then this would have been uniform, right? Now, leaving the outer surface with charge plus q because it was electrically neutral originally. Now, how would this charge get distributed on the outer surface? Huh? Uniformly. See, if this is moved no matter how, see, this distribution has to be such that it has to produce zero electric field independently everywhere inside, sigma inversely proportional to r. R is the same, so sigma has to be the same. So, no matter where this charge q is placed, whether at the center or here or there, this q will always be uniformly distributed if this is a sphere. This was the crux of the discussion, was what I spent my time on in the last class. If this q is placed at the center, then not only this minus q would be uniform, this plus q will also be uniform. This plus q has to produce zero electric field everywhere inside this region, right? If this surface was non-uniform, different r's, then this plus q wouldn't have been uniform, it would have been sigma inversely proportional to r, right? Okay. Find the potential at the center O. Hey, even if this charge minus q is non-uniformly distributed here, it produces the same potential at O as it would have if it was uniformly distributed. So the potential at O, because of this non-uniform distribution of charge, is going to be k times minus q divided by A. Because of this q is going to be kq by small r. Because of this plus q, kq by small b. Because of this plus q, it's going to be kq by small b. Even if this plus q was non-uniformly distributed, the potential at the center that it would produce will still be kq by small b. So that's the total potential produced at O. That's the total potential produced at O. Two identical conducting balls having the same charge and mass are suspended by two insulating threads as shown in the figure. These two charges, Q and M, suspended as shown. And they are in equilibrium, separated by a distance small a. Let me look at the equilibrium conditions for these. Very clearly, if I look at say this angle theta, this angle theta, if I look at the equilibrium of this, then T cos theta will balance the weight. And T sin theta will balance the electrostatic repulsion, right? KQ squared by A square. Clear? If I divide this by this, then that gives me tan theta equal to KQ squared by mg A squared. Right? Now, I will assume that theta is small. Small displacement from the vertical position. Theta is small. Very clearly, this length is A by 2. A by 2. do you see that tan sine theta by 2 is a by 2 divided by the length of the string? A by 2 divided by the length of the string, this length L. Sine theta sine theta is a by 2 divided by the length of the string, right? Now if theta is small, then sine theta is approximately the same as theta is approximately the same as tan theta. So this is approximately the same as tan theta, where A is the equilibrium separation between the two charges. Okay. So this tan theta can be replaced by A by 2L. Yes or no? This gives me, realize that mg, k and l are all constants, right? Do you then realize that the cube of the separation between the two charges is proportional to the square of the charge on each? A cubed is proportional to q squared. Everything else is this C embodies all the constants that appear here. A cubed is proportional to q squared, yes or no? Cube of the separation proportional to the square of the charges. Now that's the rule for this physical situation. That's the rule for this physical situation. Now let's look at the problem further. Now one of the balls is discharged completely. So see, there was charge q on this, and if there was zero charge here, then they would come and hit, they would collide, and they would share charge equally, q by 2, q by 2. Once they share charge equally, they would move to a new equilibrium position, q by 2, q by 2, they would move to a new equilibrium position, yes or no? Yes or no? That means in this equation, A becomes B and Q becomes Q by 2. A becomes B and Q becomes Q by 2. So A becomes B, the new equilibrium separation is C times Q by 2 whole squared. Right? Hey, but CQ squared is A cubed. CQ squared is A cubed. Yes or no? A cubed. Right? So do you realize that, or if I divide b cube by a cube, say if I divide b cube by a cube from this given equation, cq squared would get cancelled, cq squared would get cancelled, and we get 1 by 2 squared. See, cq squared would get cancelled and we'll get 1 by 2 squared, yes or no? So that means b by a would become 1 by 2 to the power 2/3. The new equilibrium separation would be the original equilibrium separation divided by 2 to the power 2/3. The new equilibrium separation would be original divided by 1 by 2 to the power 2/3, which means this operation is performed repeatedly, the same operation. So each time, so now there is a charge q by 2. Again, one charge is discharged, one particle is discharged, and then they would have q by 4, q by 4, the same operation, and then again the new equilibrium separation would be the previous equilibrium separation divided by 2 to the power 2/3. That means each time the operation is performed, the equilibrium separation dips by a factor 2 to the power 2/3. Yes or no? Each time this operation is performed, the equilibrium separation dips by a factor 2 to the power 2/3, which means after the first operation, it will become 2/3. After the second operation, it will become 1 by 2 to the power 2/3 of this. After the third operation, it will become 2 to the power 2/3 of this, up to n times. That will be the final equilibrium separation. n times? Yes or no? Each time it will dip. So the first equilibrium separation, after the first operation, it will become 1 by 2 to the power 2/3 of this. Now, after the second operation, it will become 1 by 2 to the power 2/3 of this. After the third operation, it will become 1 by 2 to the power 2/3 of this, and so on and so forth. So then, eventually, the final equilibrium separation would be 2 to the power 2 by 3 whole to the power n. That will be the final equilibrium separation after n operations.
Here, T sin theta is exerted at both ends, so this would eventually cancel. D sin theta from here and T sin theta from here.
On different particles, dude. They're not acting on the same particle, they are acting on different particles, isn't it? So they will not cancel.
टेंशन निकाल के भी फिर कर सकते थे टेंशन निकाल के
इतना टेंशन लोगे?
मतलब मैंने लिया पहली बार
तुम तो बहुत टेंशन वैसे भी लेते हो, क्यों टेंशन निकालोगे? हाँ? See, it's not like charge. Some means I'm discharging it, right? I could discharge it. I could say if there's a charge Q here, but I could create some mechanism of discharging it. I could take it somewhere else, isn't it? If this is conducting, right? I connect it to a plate with with zero potential or much lower potential. I could discharge it, right? So there would be some mechanism of discharging it. It's not getting lost, it's going somewhere else. Each of two long parallel threads carry charge per unit length lambda. The threads are separated by a distance L. Find the maximum magnitude of the electric field strength in the symmetry plane of the system located between the two threads. Okay, it's essentially like this. Just come here. Hold these two threads. Hold these two. Yeah, this is how you hold the threads. These are two infinitely large long threads, charge per unit length lambda. And halfway between them is their plane of symmetry. Right, so if the separation between them is L, then the plane of symmetry is L by 2 and L by 2 from the two lines of charge, infinite lines of charge. And on this line of symmetry between them, please, thank you so much. On this plane of symmetry, I want to find the maximum possible electric field obtained. You know what I'm saying? So just to be able to draw it with greater clarity and without clutter, in fact, let me think of the two lines of charge going into the plane of the board. These are the two lines of charge going into the plane of the board, charge per unit length lambda like this, perpendicularly into the plane of the board, right? And they are separated by a distance L. That means this is L by 2 and this is also L by 2. This is the plane of symmetry. This is the plane of symmetry. On this plane of symmetry, I want to identify a point where the electric field would be a maximum, right? Say this distance is x. This is R and this is R. Okay. So it's like this. Otherwise, why would it be not? How would it be symmetric? It is running parallelly only to the two lines of charge.
The symmetry plane also into the board.
It's going into the board only like this. So this is see again, if there is a maximum, I understand what you're saying. You're saying I could have taken this point inside the plane also or outside the plane also. That will also lie on the plane of symmetry. But realize that E would be E max. First of all, if you take points outside, then you are increasing these R's. That means you are decreasing the electric field. Right? So first of all, this distance from this line of charge, from this plane of symmetry, first of all, this R should be the smallest that you can take. If you take this point P digging into the plane, this R will increase. Or if you take this point digging out of the plane, then this R will increase. So first of all, I'm sorry, in both cases, this, if E has to be E max, R has to be the smallest it could be. Both inside and outside, we will have increase in R. Increase in R. You don't want increase in R, right? You want the smallest R. So first of all, this is the smallest R. But then this point P could also float anywhere upwards this way. That's the only thing. That means we need to model it around X. You know what I'm saying? See, this is a infinite line of charge. The field at this point, because of this infinite line of charge, is going to be lambda by 2 pi epsilon naught r. Right? The field at this point, because of this infinite line of charge, is going to be lambda by 2 pi epsilon naught r. Yes or no? Clear? This angle is theta. This angle is theta. The net electric field at this point P would be the vertical components of these electric lines, so electric field, right? Vertical components of these electric fields added up. So the net electric field would be E upwards is going to be 2 times lambda by 2 pi epsilon naught r cos theta. Right? Now this is theta. These are also theta. And this distance was x. So cos theta would be x by r. Cos theta is going to be x by r. So lambda by pi epsilon naught r squared into x. Now r would also depend on x. It's going to be x squared plus L squared by 4. This is L by 2. Right? Yes or no? So this electric field as a function of x on the plane of symmetry is going to be lambda by pi epsilon naught x divided by x squared plus L squared by 4. Yes or no? We need to find the value of x so that this is the this expression would be the maximum it could be. This is a constant, so we want to maximize this expression. We want to find x such that this is a maximum. Clear? That means we want to maximize. We want to be able to maximize x by x squared plus L squared by 4. This we want to maximize, right? Isn't it? This expression we can write as x plus L squared by 4x. Right? Yes or no? That means we want to minimize this. We want to minimize this. When this is a minimum, this ratio would be a maximum. Now x plus L squared by 4x. The arithmetic mean of these is greater than or equal to the geometric mean. AM greater than or equal to GM. Right? That means x plus L squared by 4x must be greater than or equal to 2 times L by 2. Yes or no? Isn't it? That means the minimum value of x plus L squared by 4x will be equal to L. This is the minimum value, yes or no? This is the minimum value of this expression equal to L. And when does it happen? This will happen when AM becomes equal to GM. And when would AM be equal to GM? When the quantities are equal. That means AM will become equal to GM when x is L squared by 4x. AM will be equal to GM when the quantities involved are equal. That means when x is L by 2. Yes or no? Right? Not too much of a bother, right? That means this expression would be a maximum at x equal to L by 2. And the largest value of this expression is L. The smallest value of this expression is L. So the largest value of this expression would be 1 by L, which you can plug in and obtain. So all that you need to do is put x equal to L by 2. You get E equal to E max. Or what you could have done is, you could have written x plus L squared by 4x as root x minus L by 2 root x whole squared plus twice root x into L by 2 root x, a minus b whole squared plus 2ab. This is always greater than or equal to 0. So this will always be greater than or equal to L. Yes or no? So the minimum value of this, so this is always greater than or equal to L. Do you realize that? L plus a non-negative number. So the minimum value of this expression is L. And when does it become equal to L? When this becomes equal to 0. This becomes equal to 0 when x is L by 2. Yes or no? Or if you don't like anything of this sort, or you say ddx of x plus L squared by 4x equal to 0, and you get x equal to L by 2. Yes, yes, yes. Yes, I agree with you. Right? Center O of the ball at a distance small r, that means at every point on a spherical surface of radius small r, the volume charge density is given by rho naught into 1 minus small r by capital R. Rho naught is a constant. Assuming the permittivities of the ball and the environment to be equal to unity, we want to be able to find electric field as a function of R. We want to be able to find electric field as a function of small r. Both inside and, that means for small r less than capital R and for small r greater than or equal to capital R. Let me deal with small r less than or equal to r, right? So less than r. Now, this is the surface of radius small r. This is small r. This one, just I am drawing this one separately. At small r, the electric field would be the same at every point of the surface. E would be radially outwards. Right? E and the normals are in the same direction. So the total flux through this is going to be E into 4 pi r squared. This is out of symmetry, right? So E into 4 pi r squared is the flux passing through the surface, and that must be equal to total charge enclosed by epsilon naught. Now what I do is I consider a smaller shell of radius x inside this region and of thickness dx. This is a shell that I consider in this region of radius x and of thickness dx. Right? Now the charge in this shell is going to be 4 pi x squared into dx is the volume of the shell into rho at x into rho at x would be the volume charge density at this over this dx, right? That's the charge here. The total charge is going to be sum of all of this, where x runs from 0 to small r. And now whether x or r here does not matter, right? I could have also written this as, this would be the same as 4 pi r squared rho at r dr, right? That will not make any difference in the integral when you supply the limit 0 to r. That will make no difference, right? That's going to be the total charge enclosed inside r. That's the total charge enclosed inside r, right? So rho at r, so this turns out to be 4 pi integral rho at r is rho naught into 1 minus small r by capital R. This rho at r into r squared dr 0 to small r. That's going to be the total charge enclosed in a sphere of radius small r. The total flux passing through this is going to be E into 4 pi r squared. So E into 4 pi r squared would be the total charge inside that sphere by epsilon naught out of Gauss's law considerations, and that will give me E as a function of small r. Right? Inside the sphere, I know how E is varying with small r. Clear? Now let's do that. So inside the sphere, that is for that is small r less than capital R, the flux through this chosen Gaussian surface is going to be E into 4 pi r squared. That's the flux through this Gaussian surface. That must be this charge enclosed by epsilon naught, this charge enclosed by epsilon naught, right? Rho naught into r squared minus r cube by capital R dr. R runs from 0 to small r, right? Yes or no? This 4 pi we can get taken care of. E into small r squared is rho naught by epsilon naught r squared. This would give me r cube by 3, right? This r squared, when I integrate and supply these limits, will give me r cube by 3. This r cube would give me r to power 4 by 4. Right? So for r less than capital R, E at r is going to be given by r squared. When I divide by r squared, this will become r and this will become r squared, right? So that gives me rho naught by epsilon naught r by 3 minus r squared by 4r, right? Yes or no? That's how electric field varies inside this spherical volume, inside this spherical region, right? So far so good. Yes or no? Now outside the region. See, if I have to find the total charge inside this, what would I say? 0 to capital R will give me the total charge, right? So the total charge in the spherical volume would be Q at R equal to capital R, Q at R equal to capital R, which is this expression 4 pi rho naught into integral 0 to capital R 1 minus R by capital R into R squared dr. Just replace small r by capital R, you will get the total charge inside this entire sphere, right? R squared would give me R cube by 3. This R cube would give me R to power 4 by 4R. Which is R cube by 12. Yes or no? I hope you realize this. R cube by 12. That's a total charge enclosed, right? For all points outside this spherical distribution, I can imagine this charge to be concentrated at the center, even though it's not uniform volume distribution of charge. Even though it's not your uniform volume distribution of charge, I'll just show you why I could still imagine this charge to be concentrated at the center. Can I wipe this off? See, if I look at points outside this spherical region, and I look at a small shell in the spherical region. This shell is like uniform volume charge density, rho at small r, right? So for all points outside this shell, I can imagine this shell to be a point charge at the center. So every shell that constitutes this region could be imagined, for the sake of this point, to be a point charge at the center. Therefore this entire charge could be imagined, this entire charge q at r could be imagined to be concentrated at the center. Yes or no? Right? So then if I could imagine the entire charge at r to be concentrated at the center of this, then the electric field E at a distance small r greater than or equal to capital R would be k times the charge at capital R divided by R squared. That's exactly what I was trying to explain. Every shell that I'm constructing, that's uniform, right? Because this shell inside this region is a shell of uniform volume density rho. Rho will depend only on r. So if I've constructed a shell of a certain radius, right, then all the charge on this could be imagined to be concentrated at the center for the sake of all points outside this shell. And this I can do for every shell as far as this point is concerned. So if I do it for every shell outside this point, then I can imagine the entire charge to be concentrated at the center. This entire region is non-uniform, but this shell is uniform. And this point is outside this chosen shell. So for the sake of computing the electric field at this point, because of the shell, I can imagine this charge to be at this point. And I can do this for every shell that constitutes this region. That means for the sake of this point, the entire charge could be imagined to be concentrated at the center. Yes or no? What do you say? No? Still not sure? Okay. Think of it like this. Let me explain it yet another way. This is the sphere of radius r, right? And it has a total amount of charge q in r, right? Now let me imagine a Gaussian surface of radius small r greater than or equal to capital R, right? And now at every point of this Gaussian surface, electric field will be radially outwards, and since it's the same r, it will be equal in magnitude. Yes or no? Every point of this Gaussian surface, E would be radially outward because of symmetry, because of spherical symmetry, and would be of the same magnitude because they are at the same distance from this distribution. There is no way this distribution would distinguish between this point and this point and this point and this point. So it's going to produce the same magnitude of E at every point of this surface. Yes or no? Yes. So then, the flux through this, if this surface is of radius small r, the flux through this is E into 4 pi r squared. And that must be the same as the total charge enclosed inside this, which is Q at r by epsilon naught. That means E at a distance small r then for r greater than or equal to capital R would be 1 by 4 pi epsilon naught is K. K Q in r divided by epsilon naught by r squared, which is as if this entire Q is concentrated here. The field at a distance small r would be KQ by r squared. Now do you understand this, that this entire Q could be imagined to be concentrated at the center? K. Yes or no? Clear? Where was I? So then, this is the entire charge Q, right? So electric field, which is a constant, Q at R is a constant. So electric field at a distance small r for small r greater than or equal to capital R is going to be K times, this is a constant Q at R which we have already computed, Q inside R, inside capital R, divided by R squared. It falls as 1 by R squared outside this region. It falls as 1 by R squared outside this region. Now inside the region, for small r less than R, this is how electric field varies. Rho naught by epsilon naught into R by 3 minus R squared by 4R, right? Now check this out. Inside the region, how does it vary? Let me draw a graph of this. So if I draw a graph of this, realize that E versus small r is a downward opening parabola. Do you see that? Why? Coefficient of r squared is negative. It's a downward opening parabola with roots being r equal to 0 and r equal to 4r by 3. But it doesn't go all the way to 4r by 3 because 4r by 3 is greater than capital R, right? So it goes only up to capital R, right? So electric field at R at r equal to 0, and then it's a downward opening parabola. Halfway down, see this has roots 0, this parabola has root 0 and 4r by 3. Halfway down it's going to be 2r by 3, right? So it becomes, E becomes a maximum at r equal to 2r by 3. Yes or no? Then the parabola starts to dip at r equal to capital R. It assumes a value. It assumes a certain value at r equal to capital R. And that means this is the surface. And from the surface onwards, it dips as 1 by r squared. Yes or no? This is how E varies with small r. So where is it a maximum? It's maximum at r equal to 2r by 3. At r equal to 2r by 3, which is halfway between the proposed roots of this parabola, it assumes a maximum. So E would be E max at r equal to 2r by 3. Yes or no? Without drawing the graph, you want me to do it? Okay, I'll do it. Not a problem. So let me find the maximum value of this. If you are okay with that, right? Without drawing the graph, right? That means I want to find the maximum value of r by 3 minus r squared by 4r. Right? In order that this be a maximum, ddr of this must be 0. Right? That means 1 by 3 minus 1 by 2 r by 2r is 0. That means that r equal to 2r by 3. It becomes a maximum. Yes or no? Perfect squared, you could have written this as a perfect square plus minus something. That also would work, right? So in the next problem, that is problem 3, we have an infinite line of charge. There is a charge plus q and minus q. The center of this separated by a distance d, and the separation between the two charges, say, is given to be 2L. Say I call it A, I call it B. AB is given to be 2L. Now we want to be able to find the work done in rotating this by 90 degrees. This is U2 minus U1, change in potential. It's the work done on a unit positive charge by an external agent. Whereas work done by the field would be negative of this. Right? But when they say find the work done, it means find the work done by an external agent. That means you will find difference in potential energies. So then, this is rotated by 90 degrees. A comes to this point, A prime, and B comes to this point, B prime minus Q. Right? So there is the distance of A, R1, and distance of A, R2 has changed. So the potential energy of this charge has changed. For A, R1 is this and R2 is this. For B, R1 is this and R2 is this. Yes or no? Right? So I want to find the total work done. That means total change in potential energy of A plus total change in potential energy of B. Right? Now, do you realize UA prime minus UA, difference in potentials between A prime and A. So in this case, what is this distance? This distance is D. What is this distance? D minus L. Right? So R2 is D and R1 is D minus L. So difference in potentials is going to be minus lambda by 2 pi epsilon naught log final R by initial R. Final R is D, initial R is D minus L is the initial R. Right? That's the difference in potentials between A and A prime, right? So the difference in potential energies of the charge Q is going to be this into Q. That's the difference in potential energy of the charge Q when taken from A to A prime. Right? So let's say for this system, this is delta U1, difference in potential energies of one of the charges, right? Now for B, R1 is D plus L, isn't it? Isn't it? D plus L, that's R1. And B prime, which is R2, is D. Right? So U at B prime minus U at B is going to be minus lambda by 2 pi epsilon naught log final R, which is D, divided by initial R, which is D plus L. The work done by the external agent would be this into minus Q, right? Charge is minus Q this time. This into minus Q So this will become plus Q. And that's going to be delta U2. Delta U2. The total work done would be delta U1, change in potential energy of A plus change in potential energy of B. That's going to be the total work done by an external agent if there is no change of kinetic energy. Work done by an external agent is going to be delta U1 plus delta U2, which is lambda Q by 2 pi epsilon naught log d by d plus L minus log d by d minus L. Yes or no? Which is simply lambda Q by 2 pi epsilon naught log d minus L by d plus L, as you can readily see. Right? That's the work done by an external agent. Seems good? So there is an infinite line of charge lambda 1 here, and there is an infinite line of charge lambda 2 there. Right? These are two mutually perpendicular lines of charge, and you can choose to call one of them the x-axis, the other one the y-axis. Right? And this is found to be one line of charge in that region. This is found to be one certain line of charge in that region. That means if I took a point in this, along this P, whose coordinates are x comma y, then because of this line of charge, there is going to be an electric field. Say this point P has coordinates x comma y. This will be x and this would be y. Right? The electric field at this point, because of this distance, is going to be lambda 1 by 2 pi epsilon naught x. That's going to be Ex. Yes or no? Ex would be because of this lambda by 2 pi epsilon naught x. And there is going to be Ey because of this line of charge, which is lambda 2 by 2 pi epsilon naught y. And the resultant of Ex and Ey makes an angle alpha. This is the resultant of Ex and Ey, which is along the line of charge. Yes or no? So tan alpha would be Ey by Ex. Which is going to be x by y into lambda 2 by lambda 1. Hey, but y by x is tan alpha, isn't it? Y by x is tan alpha. So I end up getting tan squared alpha is lambda 2 by lambda 1. Tan squared alpha, because y by x is tan alpha, so I get tan squared alpha is lambda 2 by lambda 1. Because y by x is tan alpha. I'm in pain today, I'll stop.